you have a molecule such as this, where so you have the longest chain is 1, 2, 3, 4, 5, 6, 7. 7 carbons. And so you're going to do the substitute of nomenclature according to that. And if you start from the right side, the first substituent chlorine is at the 3rd position. If you start from the left side, the first substituent is methyl group, which is at the 2nd position. So we are going to do it from the left side. So 1, 2, 3, 4, 5, 6, 7. So this is a derivative of heptane. And so we call it in alphabetical order 5-chloro, 2-methyl, heptane. Now, if we change the halogen to an OH group, then of course, what happens is, we write that first. Now what happens is that even though OH is at the 3rd position, whereas from the left side, the methyl group is at the 2nd position, the OH group outranks the alkyl group, and therefore we have to do it from the right side. So it's 1, 2, 3, 4, 5, 6, 7, and then we call it 6-methyl, 3-heptanol, or 6-methyl, sorry, 6-methyl heptide 3-ol. Either one of those two names are acceptable. The same way, if you have a cyclic compound, you also have to use the same kind of approach in which, like let's say, if you have a 6-member ring system, and in this case, you have, or let's make it a bromide. So in this case, you have 2 substituents at this position, and therefore we call that 1 position, 2, and 3. That means you have 3 bromo, 1 dimethyl, cyclohexane. But as soon as we put an OH group there, then the OH outranks them, methyl groups, and therefore this is position 1, 2, 3. So then it's 3, 3, dimethyl, cyclohexane, 1-ol. So that's a point to remember, that with halogens and alkyl groups, they have the same ranking, whereas the OH group is a high ranking. All right, going back to the physical properties, let's talk a little bit about solubility. again the dictum that like dissolves like, as we discussed that sometimes back, is also holds true for this type of compounds. Typically, even though you have induced dipole interaction of alkyl halides, typically dissolves only in organic solvents. They are not very soluble in water. Which is a very polar solvent. On the other hand, for alcohols, what happens is OH group, because it's polar and also it has that unique ability to hydrogen bond, the OH part is very soluble. So if you have an ROH, this is a very polar hydrophilic. This is a very polar hydrophilic group. And the alkyl group, typically, which is R, is hydrophobic. And as a result, what happens when the alkyl groups are small, they can be dissolved in water. So we know methanol, ethanol, isopropanol, these are all miscible in water. So they're miscible. Methanol, ethanol, these are all very common ones. Also, the isopropanol is actually the rubbing alcohol. And propanol, they are all soluble in water. Anything larger than that, 4 carbons and higher, typically then the alkyl chain is long enough and hydrophobic enough that they don't become soluble in water. So larger alkyl groups make them less soluble in water, but they are soluble in organic solvents typically. All right, any question up to this point? These are some of the characteristics you need to know and understand the very basics of that. But we'll emphasize next part actually, which is the more important part of this chapter. Okay, so this is the first time you're going to see a reaction. And the general reaction that we are going to talk about is essentially starting from an alcohol and converting it to an alkyl halide. So the basic reaction where R is the alkyl group, it's the ROH, and then you treat it with the hydrogen halide. X is the halogen, and R is the alkyl group. And what we get out of that is a molecule of water and Rx, where alkyl halide. But in this reaction, what is important to recognize is that it has a typical pattern that we can follow, and the pattern relates to how this reaction proceeds. And that's how we actually step by step, the reaction goes from starting material to product. One pattern that we see is if the halogen goes from typically iodine works best, okay, so the reactivity of the halogen acid is typically HI works better than HBr, which works better than HCl, which works much better than HF. So we see this pattern according to the periodic table. So as you go down, the reactivity increases dramatically. And HF is really doesn't work very well in this reaction. Okay. No other three works, okay, but in this pattern. Other thing we notice is that the reactivity of the alcohol is as follows. Typically what we see is the tertiary works best, better than secondary, which works much better than primary and methyl. To give you an example, let's say you start with very simple ebutyl alcohol. And you use hydrochloric acid. That reaction goes very rapidly even at room temperature. So use HCl. And that gives you the corresponding chloride. However, if you change the alcohol from the tertiary butanol to isopropanol, same condition, almost no reaction. If you switch the halogen to bromine, which is more reactive, HBr is more reactive than HCl in those reactions, and heat it up, then the reaction works. So we use the same isopropanol plus HBr, heat it to about 80 to 100 degrees. Then we get the corresponding bromine. Then the reaction works. But it's very important that you have to heat up the reaction. In other words, the reaction is not as active as in the first case that we discussed with the tertiary butanol. If you go to primary alcohol, then the reaction is even much worse than with isopropanol. You got to go to about 125 degrees. So there's a typical pattern that we see. As I mentioned, that tertiary works better than secondary. And by tertiary or secondary, we actually refer to this carbon. This carbon is tertiary in this case, which becomes secondary here, and it's primary here. Okay. The other carbons are not important. The important one is where the attachment to the hydroxyl group is. Okay. So why that happens, in order to understand that, we try to understand them through the mechanism of reaction. And by doing the mechanism of reaction, we can figure out how the reaction actually proceeds. Okay. And one of the things that was learned is when we also do the kinetics of the reaction, typically we can describe a rate. The rate of these reactions typically involves the concentration of the alkyl alcohol but the rate expression does not include the concentration of the acid, which means that the acid is not really taking part in the critical state of this reaction. And from that, we can postulate how this reaction goes. And this is an example of reaction, which is substitution, because we're substituting OH group for a halogen, right? So this is a substitution reaction. This is also what we call a nucleophilic reaction, and I'll explain that in more detail in a minute. Okay. We call it a nucleophilic reaction. Okay, so it's a substitution nucleophilic. And it's unimolecular. By unimolecular, it indicates that the concentration of the alcohol is important, but the concentration of the acid is not important. You can switch the concentration of the acid higher or lower, and that's not going to influence the rate. But the concentration of the alcohol is critical. And that's why this is abbreviated to what we call SN1 reaction. SN1 stands for substitution nucleophilic unimolecular. So in SN1 reaction now, let's follow the reaction using R as the alkyl group. So what happens then is that the R OH, you provide the acid here. So the acid, let's say it is HBr. So very first step is attacked by one of the electron pairs on the oxygen to the proton of the acid, which can transfer the proton. And in the process, therefore, what is generated is RO connected to two H's now. I'm not showing all the electrons involved. So this is the first step, step 1. Now the step 1, typically hydrogen transfer, okay, proton transfer reactions are very rapid. So we can conclude that this is a fast step. Now the second step, in SN1 reaction, because the acid is not really involved in this process, is breaking down of this bond between the alkyl group R and the oxygen. So this is a very slow step where R dissociates with a positive charge and a molecule of water comes out and the Br minus remains. This is a slow step. And there is a third step, so this is step 2. attacks the positively charged R. You join them with R, Br plus H2O. Step 3. And step 3 is also fast. Now the rate of a reaction is always determined by the slowest step. So the rate actually depends on the second step. Step 2 is the rate determining step. We often call it RDS, a rate determining step. And that's actually unimolecular step. Only one molecule is involved in the process of creating that bond. Now, in each of the cells, we can also think about these in terms of the energies. Now, in a crude way, let me give you an example. You have, let's say you are going from place A through D in 3 steps. Going from A to B takes you 10 minutes. But going from B to C, you have to climb a mountain. So it may take a day to get on the other side. And then a third step from C to D takes another 10 minutes. So the real rate, therefore, is determined by your climbing the mountain. If you go faster or slower in the first and the last step, it doesn't really matter that much because the other one is taking so much time. So that is what is determining your overall rate. And likewise, here also, the rate is determined by the slowest step in the process. And that's what the rate is giving you. So in this process now, you need to figure out how the energetics works. So the energetics are as follows, that you have started with where you have ROH plus HBr, and it goes to ROHH plus Br minus. So this is the first step. Second step has a high energy demand where the bond between the R and the O is broken. So it goes up here. So the energy of activation here, EA1, is relatively small. And this one is very large. And that's why it's a slower step. Gets to the intermediate where you have an R plus H2O plus Br minus. And then the Br attacks, this is a relatively rapid step, goes to the product, where this is EA2 and this is EA3. EA3 and EA1 are relatively small energy demands. This is the one that determines the rate. Get final product to R plus H2O plus Br minus. Okay. So this is the potential energy diagram of the process. Oh, sorry, this is actually oh, this is wrong. Here the product is formed, so it's RBrH2. So that's the third step. So this is how we can actually look at this reaction. And what is really important is that anything that can lower the energy of these, that reaction will go faster. Anything that would enhance the this EA2 will make the reaction go slower. So the rate really depends on this one, how high they have to climb here. And now we can see that why there is an influence of what kind of alkyl group you have. Because when we look at an alkyl group, we see that the stability of different alkyl groups are as follows. You have carbon attached to 3 alkyl groups. Therefore, each methyl group has carbon-hydrogen dipole. Okay, carbon is a little more electronegative than hydrogen, so its dipole is flowing towards the carbon. So overall, the methyl group is electron donating group, and therefore it donates the electron towards this one. And as a result, it stabilizes the positive charge. Okay. Therefore, stability of this one is higher than if you have an isopropyl group, which has only 2 methyl groups and a hydrogen. Okay. The methyl groups are much more efficient in neutralizing the positive charge or making it more stable. And if you have just one, then the dipole is only one alkyl group is donated. So the stability pattern we see is tertiary better than secondary, better than primary, and so on. This pattern is same. And so we actually probably need to discuss it in a little more detail what the effect of each of these are. Now typically we call them 2 different effects of the alkyl group. One is inductive effect. Inductive effect is essentially, as I mentioned, how the alkyl group can donate electrons. Likewise, if you put a halogen, it's going to pull out the electrons. Okay. The inductive effect is in the opposite direction. It will make it much more unstable, the carbon. Okay. The second effect is called hyperconjugation. What is hyperconjugation? It is better to express that in the valence bond theory than the molecular orbital theory, which is harder to understand. Let's look at a carbocation, and I'm showing only one of the methyl groups. So we can draw a carbocation like this, showing the methyl group. And one of the ways we can draw a resonance structure, what is also called no bond resonance, is as follows, where the hydrogen can donate its electron pair towards the carbon, which has the positive charge. So essentially then the hydrogen gets positively charged, which has no bond to carbon anymore. This hydrogen remains as such. You get a double bond here, like this. And as you can see that we can also draw similar structure with this hydrogen, this hydrogen. So each hydrogen contributes to some extent stabilizing or moving the positive charge away from the carbon, making them a little more stable. And that process is essentially a combined effect. It's a very tiny contribution, nevertheless, that stabilizes the cation, and we call it stability, as I mentioned, follows the order that where tertiary is more stable, that secondary, which in turn is more stable than primary, and methyl is the least stable of them because they're connected to 3 hydrogens. Any question? Yeah, it's one of the names given to hyperconjugation is no bond resonance. No bond because, as you see in this structure, there is no bond between the hydrogen and carbon. Okay, but it's really not very realistic, but nevertheless what it tells you is that they have the ability to stabilize in a tiny bit to donate that electron pair that is connected to the bond with the hydrogen to make the molecule a little more stable. This is actually more like an explanation than the real resonance. In the real resonance structure, you can draw the structure that are much more logical than this one. Here, the hydrogen will float away if it really happens. That doesn't happen. So it's only showing a contribution of the hydrogen. All right. So the carbon-cation stability is very critical to understand that. Now, going back to this table, this potential energy diagram, one thing we can see that this state would really be dependent on what the carbon-cation stability is. Because ultimately, when we go through this, each state has a transition state. So we call it, let's say, TS1, this is TS2, and this is TS3. Transition state 1, 2, and 3. The important one is transition state 2, because that's the one determines the rate that is the highest. So if somehow we can make this one more stable, then the transition state also becomes more stable. Or the mountain will become lower. So it's more stable, or if it is unstable, it's going to be higher. So they will have a difficult time to climb to that hill. And so if we use this analogy and just look at this part of the plot, we can say that, okay, this is really how we can describe them. The potential energy diagram for the TS2, if this is the diagram for, let's say, a tertiary carbon, okay, this is, let's say, tertiary. So the R plus is a tertiary carbon here. The secondary would be higher. And this is the secondary. And the primary would be even higher. So essentially then, it becomes more and more difficult